Okay, so after this technical challenge, let me thank the organizers for organizing the conference and maintaining it online. It's a great pleasure to be in SIAM and a huge honor to start the conference. So I'm going to talk about the geometry of time clusters in the infinite Ising-Weighted Triangulations, and this is a joint work with Laurent Ménard, who is currently in Shanghai and in the Zoom. So, because I'm starting the conference, I feel that I'm allowed and entitled to give the definition of a planar map. A planar map is a proper embedding of a planar graph in the sphere, considered up to orientation having here different drawings of the same map. And it's a different notion from a graph, because here you can see that if you look at the planar embedding, it fixes the cyclic ordering of the vertices of the neighbors of the vertices around. So here, for example, around this vertex, its neighbors don't appear in the same cyclic order around it. Here, in a combinatorial setting, a planar map is a planar graph with a fixed cyclic ordering of the vertices of the neighbors around each vertex. So here in my talk, to avoid dealing with symmetries, all the maps are going to be rooted. So I'm going to have a distinguished Marseille, which is represented by two arrays like that. And M is going to be the set of. An important point of view in this talk and in the study of maps is to view the maps as the metric spaces, where the points of the space are the vertices of the map, and the distance is just the graph distance. So I'm only going to consider graph distance between its two fixed points. And I'm going to talk today about triangulation. So triangulation is a map where all the faces have degree 3, and the number of edges in the triangulation is necessarily a multiple of 3. So when I'm talking about triangulation of size n, it's going to mean triangulation with 3n edges, or equivalently with n plus 2 vertices or 2n faces. You have only one relevant parameter for the enumeration. And a bit of technicality, I'm going to talk a lot about triangulation with a boundary, just a different family of planar maps where all the faces are triangles, except possibly one outer face, which is allowed to have any length. Here, for instance, I have a triangulation with a boundary of length 4. You can see that the external face here, the outer face, is of length 4. These objects are going to appear naturally in the talk. Okay, so one of the points of this talk is to somehow answer modestly to the question, what does a random triangulation of size n look like? So it's the question which has been under a lot of investigation in the last 20, 30 years, or even more. And you have two main points of view to answer these questions. And the first one is the so-called local limit point of view, where you sit on the root vertex and you only see what happens at a finite size. You only see a portion of the neighborhood of the root vertex. Another point of view is a scaling limit point of view, which I will discuss a little bit at the end of the talk, is to renormalize all the distances to keep a bounded compact object. Yes, so today, the main point of view of my talk is going to consider a local limit point. Okay, so a bit more precisely, let me define the local topology, what I mean by the local convergence. It's also called the Benjamini-Schramm convergence. So the idea is the following. You consider a rooted planar map like that, which is rooted, so it has a root vertex, a huge vertex here. And you can consider the ball of radius r around this vertex. It's made of all the vertices which are distance less than r from the root vertex. Okay, so let me label all the vertices by their distance to the root vertex. So its neighbors are labeled 1 and the neighbors of 2. And this is the ball of 2. And the local topology on a set of rooted planar maps is just defined, is induced by the following distance on map, which is to say that you consider, given two maps, two rooted maps, you're going to consider the maximal radius on which they agree, the maximal radius for which you cannot tell apart the two different maps, and the distance is basically the inverse of this quantity. Okay, and this is distance on planar maps, and it defines the local topology, and it defines, a topology, and this is the local topology. So saying that a sequence of maps converges to the local topology means that for all fixed radius, their balls of radius r are going to be equal for n sufficiently large. Okay, so here we consider, so this is for deterministic maps. So here I'm going to consider random maps in a minute. And so it's exactly the same thing. You have measure on random maps and saying that the sequence of measures converge for the local topology is just to say that the sequence of probability measures converge in distribution for this local topology. Okay. Like issue with my this is right. So in 2003, Angel and Schramm proved that for if you consider use a uniform measure on triangulation, so remember the set of triangulations with 3 n edges, the finite set, you just take the uniform distribution on this set, and they proved that the distribution converges in the sense of the local topology towards an uniform, towards an infinite triangulations, or more precisely, a probability distribution on infinite triangulations that they call the UIPT for uniform infinite planar triangulation, okay, which is a measure supported on infinite planar triangulation. So here are two representations of the UIPT by Igor Kochemsky or by Timothy Budd. And just to give you an idea of what this object looks like. And since the work by Angel and Schramm, there have been a lot of work about to study the UIPT and describe its properties. And now it's a fairly well understood object. And in the initial work of Angel and Schramm, they proved that the UIPT has almost only one end, so meaning that it's an infinite two-dimensional object. Okay? And you can ask, where is the infinite? Where is the infinite part? Where does it lie? And saying that it's one-ended means that if you remove a finite part of the infinite triangulation, a priori you're going to disconnect the triangulation into parts. So for instance here, if I remove all the faces that are colored, you can see that I'm going to have different connected components, which are the faces which are white, and you have several connected components. Being one-ended means that only one of these connected components is going to be infinite. Okay, so you have here small parts of the triangulations, but only one here, the outer, which is in the outer region, is going to be infinite. Okay. Angel in 2004, and then some result by Nicolas and Jean-François, managed to characterize and give very explicit formulas for the volume and the perimeters of the ball of radius r in the UIPT. So in the UIPT, the volume scales. I'm not giving you here the more precise results you can have, but the volume of the ball, which is important, you can see that they scale as r to the 4. Okay? So you could expect that in a Euclidean, a two-dimensional setting, you have r squared, but maybe you have a fractal effect r to the 4. And we have also a bit different type of result obtained by Gorel, Gorevich, and Narmias, where they proved that the simple random walk in the UIPT is right. Okay, so you have all these properties about the UIPT, so, which is now really fairly well understood. You have a lot of tools to study it, a lot of results available. And a very important point here, which is going to matter for the rest of the talk, is that we expect this kind. So we study triangulation somehow because they're easier to study. And the important point here is that we expect the same type of behavior for other models of random maps. So you rather study triangulations, then somehow the same type of results are going to happen. Of course, you're going to have maybe different constants here, but the big picture is going to be the same. You're going to have the same volume exponent. The ball are going to scale as r to the 4. And this is actually proved for triangulations by Krikun. But you take any reasonable model of map, and the same type of result is going to happen. Okay, so it was fun for a while to find different models which admit the same behavior, but after a while you get bored and you want to see something different. You find another model, and the question is, what does it take to see something different? Okay, how should you tweak your distribution on map to see something which is different from this behavior, where you don't have typically the r to the 4 for the volume graph? So it has been understood fairly long ago that to obtain such behavior, you need to consider maps where you also have coupled maps with a statistical physics model. In the more physical term, it's called coupled gravity with matter. Gravity is going to be the random map, and the matter is going to be the statistical physics model. Okay, so that's why I'm going to define now a statistical physics model on my maps, which is the Ising model. So first, I'm going to define the Ising model on a finite deterministic planar triangulation. I have a triangulation here, just a finite triangulation, and I'm going to decorate it by a spin configuration. By that, I mean that I just choose for each vertex a spin which is either +1 or -1. And sampling an Ising configuration on this map just means to take a spin configuration with a probability which is proportional to this probability here. Okay? So this is a physical formulation, the way it's usually written when you take any book and about the Ising model. But in our setting, it's completely different, completely equivalent, than to have a more combinatorial formulation and to say you fix a parameter nu, and you're going to sample a spin configuration with a probability which is proportional to this parameter nu to the number of monochromatic edges. So monochromatic edge is an edge where both spins on its extremities agree. Okay, so here, for instance, I have 5 monochromatic edges, which are the edges in a flat blue here. And so I'm going to sample this specific configuration with a weight which is nu to the 5. Okay? And it's just a simple change of variables between the 2 points of view. It's completely equivalent. Okay, so this is for a fixed triangulation. If I have a fixed triangulation, I can sample an Ising model on it. But what I want to do, I mean, I explained to you, what I want to do is really I want to change the geometry of the triangulation. I want to see balls which have red volume of different type, with a different volume of growth. Okay, so what I want to do is actually, I don't want to fix the triangulation. I want to sample at the same time the triangulation with the Ising model. Okay? So the idea is now to consider, again, triangulation of fixed size with size n. And now I'm going to consider a triangulation with spins with a probability, which is this one. So I'll still have the nu to the power number of monochromatic edges. I'm just restricted my attention to the triangulation of this n. And I'm going to sample a triangulation with spin with this probability. And I'm going to normalize it just to have a probability distribution. So, I mean, so far it's very easy probability. I mean, it's a finite triangulation of size n. It's a finite set. So I'm just doing like discrete probability. I have no issue of normalization. I mean, everything is finite here. I have finite sums, everything is finite, everything is fine. Okay? And important point, I mean, I'm a bit heavy on this, emphasizing once more. This is a probability distribution on triangulation with spins. But if you consider the push forward, you forget the spins and you look at the push forward on triangulations, it gives you a distribution on triangulation which is different from the uniform distribution. Except if nu is equal to 1. Okay, if nu is equal to 1, then you get the uniform distribution. But otherwise, you get a different distribution. Okay. So why? So I told you that's an intuitive way of doing things. It's a good idea to consider this type of model. Okay, but it was a bit vague, and let me motivate a bit more why this is a good idea to consider this model if you want to see something different from the universal behavior. So if you look at maps like undecorated maps, regular maps without Ising model, you have a lot of enumerative formulas available. I'm not going to cite them all. And for triangulation, you have explicit formulas. For triangulation, for general maps, you have a lot of formulas. And in all these cases, you can look at the asymptotic enumerative coefficients, and they all behave in this way. You have a constant, you have a row to the -n, so an exponential term, and then you have a polynomial correction, which is always of the form n to the -5/2. Again, the same polynomial correction is universal. It doesn't depend on the precise family of maps you consider. Okay. Now, if you look at Ising-Weighted Triangulations, you can look at the generating series. So I'm considering this series, which is just the sum over all triangulation, the sum over all the spin configurations, and I give to each decorated triangulation a weight which is nu to the power number of monochromatic edges and the t to the number of edges. If I look at the coefficient in t, the coefficient in t to the 3n, this quantity here, this is actually exactly this normalizing coefficient. That's introducing something new here. you can look at the behavior of this coefficient. Okay? So this is the analog of the number of triangulations, if you want. It's the total Ising weight of triangulations of this. Okay, so there were work by Bernardi and Busquemelu, and they proved, they studied this generating series, and they proved that it's algebraic, and it allows them to obtain the following asymptotic behavior for this coefficient. And for almost all value of nu, you see exactly the same universal behavior as for undecorated map. You have the -5 half. But fortunately, there is a special, a critical value of nu, which is 1 + 1/7, where you see something different, where the exponent change and you have -7/3. Okay, so there's some combinatorial evidence that something happens at nu c. Okay, and the existence of this critical point was first observed in the physics literature by Bulatov and Kazakov in the 80s, and this was also re-derived by bijection with trees by Busquemelu and Schaeffer and by Di Francisco and Guillaume. Okay? So the fact that this critical value of nu exists for the Ising model is no big news. It has been around for a while. Okay? And this suggests really that there is something different happening at nu. Okay, so let's try to study this Ising model then. So what we did in a previous work with Laurent and together with Gilles Schaeffer is that we prove a result which is fully analog to the one obtained by Angel and Schramm that I discussed at the very beginning. So we proved that there is a convergence. So you take your distribution on Ising-Weighted maps, and we prove there is convergence for the local topology towards an infinite limit. So now what we obtain in the limit is a probability distribution, an infinite triangulation with an Ising model on them. Okay? So with what we call with the new IIPT for infinite Ising planar triangulation. And let me mention that there was a recent result by Lin-Chao Chen and Jonas Turunen for slightly different models, where they consider a model with different boundary conditions. So what can you say about the new IPT? I told you that the UIPT is very well understood now. Picture is a bit different for the new IPT, which we don't understand so well its properties, but what we can prove is that it's one-ended, most surely. We can study also the simple random walk and prove that it's a recurrence. So it's similar to the UIPT. Something we could do is a geometry of the clusters, and this is what I'm going to do in a second. What we would really like to know is what the volume of its balls. I mean, see something different to the R⁴ that I told you about. We expect a different behavior when nu is equal to nu c. There is some conjecture in the physics literature. There's Watanabe's conjecture. The status is unclear, let's say. It's not really clear if people believe it or not. There are some bounds though which agree with it. So, but somehow we expect something which is of the order 4.21. Way. We expect something different. I'm not going to prove anything related to this conjecture in this talk, but what I'm going to do is to look at the geometry of it. Okay? So let me talk a little bit about that. So our idea is to, so we see that something, combinatorially at least, we see that something different happened at nu c. And what we would like to see, what's interesting here in this result is that we have a convergence for every value of nu, not only for nu c. Okay, so we can really look at the phase transition in the infinite object. Okay, and this is what we're going to do. We're going to look at the geometry of the clusters for all value of nu, and we are going to be able to really see a geometric phase transition. Whereas before it was maybe more combinatorial phase transition. Okay, so before stating our result, let me just give a bit background on what happens on D2. So if you consider an Ising model, but on a deterministic lattice, D2, rather than a random lattice. And this could be seen as a ultimate goal for what we are doing. So on D2, the picture is really well understood. It has been studied for a while. And here I have some simulations by Raphael, which illustrates the different possible behavior. So when nu is bigger than nu c, so when you have a huge weight on monochromatic edges, somehow spins tend to agree. And what happens is that you have an infinite cluster. You have one infinite cluster, so you have one spin which is going to dominate everything, basically. Okay? When nu is equal to nu c, you can see that it's not completely evident on this picture, but there is no infinite cluster. I mean, it depends a little bit, but there is no infinite cluster. But somehow you can see that there is some long-range interaction. And it was proved that you can look at the boundary of the cluster. You can look at the what happens at the interfaces. And it was proved by Felkak and Smirnov that you have convergence to CRE3. I'm not going to enter into any details here, just to give you some ideas about what's known on this. And in the subcritical setting, when nu is less than uc, so I told you that you have nu equal 1. Nu equal 1 corresponds in our setting to uniform triangulations. It also corresponds, I'm going to come back to that in a second, to a critical percolation. So for nu subcritical, you expect to, again, I'm going to give more precise statements about that, but you expect everything to behave as critical percolation. And for critical percolation, it was proved by Smirnov that the interfaces scale as a CLE6, and in particular, it is also known, much weaker result, that there is no infinite cluster almost. I'll come back to some analogs of this result for the Ising model on random map at the end of my talk. So we don't obtain any, so what we obtain is much weaker than this kind of statement. But here you see that there is really a phase transition. You can see really on this picture that there is a geometric phase transition about the behavior of the clusters. And what we proved with Laurent is somehow one of the results we obtain is a similar evidence for a phase transition. We look at the cluster, the root cluster, and what we proved is that for nu less than uc, there is no infinite cluster with almost surely, and that for nu bigger than uc, I mean uc is a for nu equal uc, there is no infinite cluster, and for nu supercritical, there is an infinite cluster with positive probability. What's nice in our result, and I come back to it, is that we actually, in the supercritical case, we obtain a fairly explicit probability, a fairly explicit formula for the probability. And in particular, it enables us to study exactly what happens just above nu c and to compute the so-called critical exponent in this case. So we can prove that when you go very close from nu c, you have this kind of dependency of the percolation probability in terms of u. And just for the record, on Z2, the exponent is known to be equal to 1/8. It's an older work by Untitled and Young, the 45th. So it's quite nice to have somehow the analog, random stuff. Okay. Yes. Yes. I don't know. Okay, and so that was really evidence of the phase transition for the percolation of the probability of percolation. And we also have some quantitative results about the geometry of the clusters, really. And so what we can prove is that in the subcritical case, so when the root cluster is finite almost surely, we can also compute the tail distribution of its volume and the tail distribution of its perimeter. So just to fix really this, because I'm talking about the sign clusters for a while now, and I haven't defined it very well properly. So if I have an Ising-Weighted Triangulation here, which is rooted at this edge, what I call the sign cluster is really the connected component of the root vertex when restricted to monochromatic edge. Is this map here. And delta C is the length of the boundary of the root cluster, which is represented by these blue edges here. So somehow the volume, this gives you somehow the area, the volume of the root cluster, and delta gives you somehow the length of the interfaces between a different cluster, which are two quantities which are relevant studies. Yeah, so we can basically compute and rest. So before giving you some idea of how we can prove such results, I want to spend just one slide on the special case nu equal 1. So for nu equal 1, recall that the probability distribution I consider is this one. So when nu equal 1, these terms basically disappear. And you see that every triangulation of fixed size with any given spin configuration is sampled with the same probability. Okay, so in other words, it means that you sample a uniform triangulation where each spin is +1 or -1 independently of the others with probability 1/2. It's really a percolation of parameter 1/2 on the random uniform triangulation. Okay, and I told you that Angel studied, I didn't tell you, but Angel studied triangulation, percolation and triangulation, and he proved in 2004 that the critical parameter for percolation on the UIPT is 1/2. So what we have here is exactly a critical percolation on the UIPT. Yes, it's a very specific point of the model we study is a critical percolation on the UIPT. And a percolation on the UIPT was studied by Olivier Bernardi, Nicolas Curien, and Grégory Mirmont via its clusters. Yes, somehow we retrieve in our work the result they obtained for nu = 1, and we. And somehow our results reinforce the idea that I mentioned a bit before that nu = 1 doesn't play any special role here. I mean, if you look at my exponents, nu = 1 is here, and you see is a 1 plus 1 over square root of 7, so it's bigger than 1. Nu = 1 is here, and you see that it doesn't play any special role. So you really have the idea that Ising in the subcritical case really corresponds to critical percolation, and there shouldn't be any special role played by critical percolation here, which is something which is widely believed to be true, but for which we don't have any some rigorous indication. Okay, so now let me give some ingredients of the proof of our result. So the starting point of our result is the Gasket Decomposition, which was introduced by Thierry Boutier, Gaëtan Borot, and Emmanuel Guiter, and which was used also and derived in Bernardi and Curien and Mirmont. So the idea is to start from this Ising triangulation here and to consider the cluster of the origin, which is the map spanned by the monochromatic edges, and which the connected components. Sorry, the connected component of the map spanned by the monochromatic edges and which contains a red vertex. Yes, so this map in fat blue edge. So if I give you only this map, only the fat edges, and you want to recover the original map, what you want to know, what you need to do, sorry, is what you plug inside. So if I just cut along here, you need to tell me what I need to add in each of the faces of the cluster. Okay? In other words, if I give you just that, for each face, for example, for the face A, you need to tell me what I'm going to glue inside it. Okay? And you need, only did it for 2 faces because otherwise it was just unreadable, but you need to do that for every face of the cluster. And you can see that because you only span monochromatic edges, of course, every edges which are going to be incident, which are going to be inside this space, but incident to a vertex which lies on its boundary is going to be a non-monochromatic edge. Otherwise, it would have been kept in the cluster. Okay, so somehow you have a security parameter here, which is made of non-monochromatic edges. And it's a nice term for that is a necklace. Introduce the decomposition. So you have a first part in these spaces, which is a necklace made of non-monochromatic edges. Okay? And then you have and then what you have in the inside of the necklace is a O, where you have only minus spins, and here you need to glue the rest of the triangulation. So now you're going to glue a triangulation, an Ising-Weighted Triangulation, with a monochromatic boundary condition. All the spins on the boundary are going to be minus spin. Okay. These are parts are called the I. Okay. So now suppose I want to compute the probability that this cluster arise in my triangulation. So in other words, what I want to compute is I want to compute the total weight of triangulations, the total Ising weight of all triangulations which admit as a sign cluster this map. Okay? What I need to do is I need to compute the total weight of the submap I can plug in all the faces of its cluster. Okay? Let's do that. So I have this quantity, and I'm going to. So I told you that it's a product of the faces because I need to plug in each face. So the first contribution really comes from the edges which are going to be present in the cluster. So some edges are present in the cluster. Okay, so they are in the initial triangulation and they stay in the cluster. So I need to account for this edge. These edges are monochromatic, so they need to be counted by a weight nu because they're monochromatic and t because they are edges. Okay, so I need to count nu t for each of these edges. And because each edge belongs to two faces, they have to be counted once, square root of nu t on one side and square root of nu t on the other. So this is why I have these terms here to account for these edges which are on the boundary of what I put. Okay. Then I have to account for the weight of the ions. So they are monochromatic, Ising-weighted triangulation with monochromatic boundary. Okay, so I need to introduce this generating series, which is generating series of triangulations with a monochromatic fixed boundary. Okay, and L here, L is the length of the boundary which I have here. Okay, and then I need to count on all the my security region necklace. I need to account for all the edges which are here. All these edges are non-monochromatic, so there is going to be no nu here, only t to the number of the power the number of to the t to the power the number of edges, and this is just given by a binomial coefficient. Okay, so such a decomposition really already appeared in the two papers I mentioned. And if you put everything together, you obtain that the weight, the probability to see a given cluster is going to be given by a product of weight, where you have a rather explicit formula, so QK. I'm just going to, can I write on the board? Just for the record. So that I'm going to make anything very precise on this weight. But did I do? I'm just going to, can I do it? Not, okay, yeah, I first, okay, I have just a dummy term if k is equal to 3, but what's important is this part. I don't. Okay, I'm not going to pick another chalk. It's just too risky. Say, this is a generating series of triangulations with a boundary, and where the boundary is of size L. So we have this sequence of weights which appear naturally when we are doing the cluster, the gasket decomposition, and now it can go away. And say, why is it nice to put it in this setting? Say, it's very nice because now we can see the cluster as a Boltzmann random map. Okay, so the Boltzmann random maps is just a probability distribution on maps, which have been studied quite a lot last years, and which is defined as follows. So you have a sequence of weights qk, and you sample a map with a probability which is proportional to the product of q indexed by the degree of the face. Okay, so exactly what's written here. And if you want to be able to define a probability distribution from this idea, you need to be able to renormalize it. So you just need to be able to prove that this quantity is finite, so you can turn this rough definition into a proper distribution for probability distribution. Okay, so and then we can rely on many works about the behavior of Boltzmann random maps, which were introduced, I think, by Barca and Miamon at the beginning, then studied by Grégory and Jean-François, and then also in this paper by Boro-Boutillier, and a lot of results by a very general setting by Marzouk. And these papers may all rely on an encoding of the map by a tree via the so-called Boudier-Di-Francesco-Guitta bijection, where the degree of the face are encoded by the degree of the vertices in the associated tree. So that's why, I mean, when you look at Galton-Watson tree, you have a fairly good control about the degree of the nodes, and this gives you some similar control on the degree of the face in the corresponding map. That's why we have this very natural setting for maps which emerge from what we know about Galton-Watson. Okay, so I told you that these maps have been studied quite a lot, and some of the possible classifications, the possible behavior are now fairly classified, and we can just try to decide in which case we. So, not going to give too many precise definitions, but we consider distributions which are critical, meaning that the expectation of the size is finite, but the variance of the size is infinite. And you have two possible cases, depending on whether the probability of the degree of a typical face is to be big, decrease exponentially, or decrease polynomially. Okay? In a very rough way of describing things, it tells you whether you're going to see somehow the faces in the limit or not. If you have a very strong exponential decrease of the degree of the faces, in the limit, somehow, when you look from afar, you're not going to see the faces anymore. They're going to disparate in the scaling in a way. And this is a realm of the Random Map. I'm not going to enter into much. And whereas when you're non-regular critical, meaning you have only polynomial decay for the probability, then these faces are going to exist in the limit. What happens in our setting is that for new supercritical, we are here. So we have a polynomial, we have exponential decay for the probability of a face to be large. Whereas when U is not bigger than UC, we fall in this regime where the Boltzmann map associated to the cluster is non-regular. And this is what I would. And so we can study the clusters thanks to this classification. For new supercritical, as soon as we have this result, the fact that there is percolation with positive probability comes fairly easily from the work by Bernard and Mirmont, because by exactly the same type of argument that they use, we can prove that there is existence of an infinite cluster with positive probability. It doesn't give us the really explicit form of the probability that we have. It gives us somehow the fact that there is a cluster with positive probability, but not the expression for this probability. And say, to be able to prove this result, so we need to say in which setting we are, so whether we are regular critical or non-regular critical Boltzmann map. And of course, this behavior depends on the weight and depends on the asymptotic properties of the weight. And if you look at the expression for the weights, you can see that the expression we have for the QK depends really on this QL class here. Okay, in a bit cumbersome way, but still, I mean, to have any hope to investigate the property of this sequence of weight, you should start with having some asymptotic properties for the QL. Okay, so the first step should be to study this generating series. Yep. Yeah. 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 UC is 1 plus. Should be enough for our purpose. Yeah, exactly. Yeah. Yeah, exactly. The idea is to really study to have a full understanding of this Q plus. So how did we do that? So it relied, in the previous paper with Schaeffer, we obtained an algebraic equation for Q plus. And in the paper by Bernardi and Busquet-Melou, there was a rational parameterization for Q1, so only for a boundary of length 1. Okay? So here you see we have two variables. Huh? We have T, here, which is the size of the map, and we have y, which is the length of the boundary. Okay, so we have Q1 is fine. And we also have an algebraic equation for the full series with both variables. Okay? So what we did is that we took in the algebraic equation we have here, we replace T by its parameterization given by Bernardi and Bustamante. Okay, so we get rid of T. We only have Y cup. Okay? And then you can ask Maple to compute a rational parameterization. You have an algebraic equation, which we had. Okay? But then it didn't work because there is this new. The Maple just after 3 hours doesn't give you anything. We stopped, killed it. And so what we did is we tried just for different values of nu. We took like nu equals 4, nu equals 5, nu equals 6. And then Maple does give you a rational parameterization. And then the job was to just make all these rational parameterization which were different, like consistent one with another. And work then to make, because Maple is not really smooth, the rational parameterization he gives in quite not so nice formulas, and then with some work you can make it a bit nice, and then you can get a rational parameterization. And when you have a rational parameterization, it's fairly okay to compute the assembler SMA. It does require some work, but it's doable. And this approach was also used by Jonas and Hennenfent in their paper. It's a very similar way of proving. Just to give you an idea of what it does look like, here is a rational parameterization we obtained. So this is a rational parameterization obtained for T by Bernardi and Bustamante. So P here is a polynomial. Okay, so we have that. This is a rational parameterization. So you can see the rational parameterization is just a change of variables. I replace T by U, and I'm going to replace Y by V. And this is the dependency between V and Y. Okay? And this is then the expression of Q in terms of U and V. Okay, it is what it is. But it's not ugly. I mean, like, it depends on your notion. But it's a polynomial. You can just study the denominator, look at the poles, and do whatever you want, really. And then I'm going to spare you and not giving you any more idea of the computations. But then the idea is just to say that the probability that the cluster is finite is just summing over all the finite maps of the probability that the cluster is this fixed map. And then we can prove that it's 1, nu is nu less than uc, and we can prove an explicit formula when nu is bigger than u. Okay? We have an integral formula. The proof is rather technical. I'd be happy to discuss it with anybody which is interested. But it's not really presentable. Okay, so it's how we do it. Okay, and we obtain, I mean, by the same type of method, we obtain similar estimates for the size of the clusters. I told you a little more about the infinite setting because I think it's where the results somehow are crisper. You have an infinite cluster or you don't have an infinite cluster, but we have really similar tail experiments for when you consider slightly different models. For example, you consider triangulation of fixed size, or if you consider Boltzmann triangulations, that is maps which are of random size but finite random size. And in this case, we can rederive all the tail experiments for the volume and parameters. And we recover in particular the results obtained in Bernardi and for percolation. And also our experiments are in agreement with the ones computed by Borobuté-Guiter for the ON model, because there are some connection between the ON model and the Ising model. Everything matches. And we can also say, I mean, based on all these enumerative results we have, we can also compute the geometry of the interfaces in the loop trees vocabulary produced by Nicolas and Igor. And just the proof go through somehow because we have all these nice enumerative results. Okay, I just I started a bit 3 minutes more. I just wanted to give you some maybe a dream scenario, something like that, some perspective, and the links with Liouville quantum gravity. So I'm going to be very elusive here, and just to give you some connections and what our work is related to. Let's say again, very elusive. Okay, the gamma Liouville quantum gravity is a random the measure on a surface, a random measure on a surface, which is defined as the exponential of the Gaussian free field, where the means that this definition does sense, but which was constructed rigorously by Duplantier and Ship. They give a rigorous meaning of this non-rigorous definition. And map, uniform map, triangulations, without the Ising, matter without matter, so uniform map, converge to the square root of 8/3 trivial quantum gravity. So I'm not going to recall all the steps of this result, but it started with the work of Grégory Mirmont and Jean-François Le Gall about the convergence of rescaled maps, the fact that the scaling limit of map is the Brownian sphere, and then the characterization by Miller and Sheffield, the correspondence between the Brownian map and the square root of 8/3 trivial gravity. Okay, so you can, through this path, show that the scaling limit of map without matter is a square root of 8/3 trivial quantum gravity. It's a very, very fast way of describing this result. Okay, so this is the Brownian map, so the scaling limit of triangulation. This is the square root of 8/3 trivial quantum gravity. So this is a random metric space. This is a random measure on the sphere, and somehow you can map one onto the other. Here it's a way of uniform triangulations embedded on the sphere via a circle pack. Okay, that's the canonical way to draw a random map on the sphere. Okay, so this is established now for uniform map. But the truth is that we expect such results to hold for every statistical physics model on random geometry. Okay, so we expect that if you define a statistical physics model on a map, then it's going to converge to a gamma LQG for an appropriate value of gamma. Okay, and for critical Ising model, this exponent this gamma is supposed to be square root of 3. Whereas for non-critical, you expect to have the same behavior as for uniform maps and recover the 8/3. Okay. You can also wonder, okay, this is what the scaling limit should be, but what about the clusters in fact? What about the clusters? Can you see the cluster in the scaling limit? Can you see the interfaces of the cluster in the scaling limit? And I told you at the very beginning of the talk that in the Euclidean setting, it was established, at least for critical percolation and for the critical Ising model. Okay, you have CLE6 and CLE3. And we expect the same to hold somehow for the quantum counterpart. You expect the same to hold for statistical physics model on random maps. You have the interfaces described by CLE6 and CLE3. For critical percolations, corresponding to nu equal 1, this has been established by Orden and Sen in a very, very nice result where they were able to really prove convergence in a strong sense of a triangulation with a critical percolation. So they proved the result for critical percolation. Okay. What about Ising? So we are far away from establishing such a result for Ising model. Okay? Very, very far away. But if the conjecture is true, then you expect to be able to relate the volume of the clusters in the deterministic setting, Euclidean setting, to what happens in the random map set. So you expect the volume of the clusters to be related with what is the so-called KPZ relation. And you can compute them. You can compute, okay, if the volume of the cluster is something in the Euclidean setting, it should be something in the quantum setting. And the KPZ relation is for gamma duvet quantum gravity, and it depends on gamma. So I told you that for gamma, for the critical Ising model, gamma is supposed to be square root of 3. And so what we can do is that we compute, thanks to the exponents to compute, we can compute the perimeter and the volume of the cluster in our model, and you can relate them to the known value on the Euclidean. Okay? And okay, it's like math. But it's not a contradiction to the conjectures. Like it's a good point. So we didn't disprove the conjecture. We didn't prove them either. But it's a nice. Okay, it was a very fast transition with LQG. But I can discuss more about that if you want to. And I'm going to stop here. Thanks a lot.